Okay, so I'm going to describe the radioactive decay process, which is used in radioactive age dating of everything from remains at archaeological dig sites to the ages of rocks on Earth to rocks from the moon and from meteorites to determine the age of our solar system. And rather than start off with some sort of gory nuclear physics, it's much better to think of a simple example that illustrates the quantitative behavior. So what I want you to do is think of self-popping popcorn. So you can imagine I have a kernel of popcorn, and it's self-popping in such a way that it has a 1 in 10 chance per minute of popping. So if I just set that one kernel down on a table and watched it, I would know that there's a 10% chance per minute it would pop, so I would expect it would take 10 minutes for that kernel to pop. It might pop a little sooner, it might pop a little later, but on average it's going to take 10 minutes to pop. So now imagine I take a jar and I fill that with 100 of these kernels, and then I seal up the jar and set it down and watch it, and let's see what happens. Well, what's going to happen over the first minute? Well, I'd expect, since each of those has a 10% chance of popping, that 10% of the 100 kernels in there would pop. So I'd have 10 popped kernels and 90, or 10 popped popcorns and 90 remaining unpopped kernels. And then, well, okay, what about over the next minute? Well, I'd have 90 kernels, and I'd expect a tenth of them to pop, so I'd expect 9 pops in the next minute, and that'd bring me down to a total of 81. And I could keep doing this calculation, and eventually you're going to be down to a point where, say, we have 10 kernels left. We have 10 kernels left. I expect over the next minute that one of those kernels would pop, leaving me with 9. And then over the next minute, there'd only be a 90% chance that I'd see any kernel pop at all. But eventually they would continue to keep popping until I got down to one kernel. And then when there was that one remaining kernel, it would be just like the initial case I talked about, where I would expect that would decay or pop in over about 10 minutes. So I started off with a jar full of 100 kernels. There was a lot of popping early on in the first few minutes, and then that popping rate went down and down over time as the number of kernels remaining went down and down over time. And in fact, I can illustrate this with a graph just showing you that popping process. So looking at the number of kernels remaining over time, when each kernel has a 10% chance of popping per minute. And now how is that going to help us get at determining the age since I sealed in the jar? Well, let's begin by asking how long does it take for half of the kernels to pop? Well, you could look on the graph here and see that after about 7 minutes, half of the kernels have popped. Okay, now we can think, well, from that point of having 50 kernels remaining, how long will it take until I lose half of those again? Well, we can look on the plot and see it takes about 14 minutes. So another 7 minutes. Okay, well now I have 25 kernels remaining. Alright, of those 25, how long will it take for half of them to pop on average? Well, I can look and see again another 7 minutes, total 21 minutes. And in fact, that process continues on down the line and is a general feature of any kind of decay process where the chance of popping, if you will, is just constant over time for any individual kernel, and you just have a large collection of those kernels. Or in other words, we can say however many kernels you have, it's going to take 7 minutes for half of them to pop, right? And this is the notion of a half-life. So you can see that initially here, the graph I had, it had 100 kernels, right? The example was 100 kernels put into a jar, but that could have been any number. That could have been 500, And you can do the exact same calculation. Well, in the first minute, you'd expect to lose 10% of them, or 50, and that would bring down the total to 450, which is still 90% of the original amount. Likewise, you keep doing that same calculation on down the line, and after 7 minutes, you would have lost half of the kernels. Same if it was 1,000, same if it was 5,000, same if it was any number. So really, we can just think of the half-life as the amount of time it takes for half of the kernels to pop, which in this case is 7 minutes. So back to, how does this help us determine the age, or the amount of time that it's taken since the jar was sealed? And I put in all those unpopped kernels. Well, if you look at the ratio of the popped kernels to unpopped kernels, you can determine how long that jar has been sealed. For example, I bring out a jar with these kernels in it, and 3/4 of it is popped popcorn, and 1/4 of it is still kernels. How long has that jar been sealed? It's going to have been sealed for 2 half-lives, which in this case is 7 minutes, so it would have been sealed 14 minutes ago. So I know that after 1 half-life, I'd have lost half of it, so there would be an equal ratio to kernels and popped popcorn. And then after another minute, or another 7 minutes, another half-life, I'd expect half of the remaining kernels to pop, leaving 1/4 of the original amount. So that ratio, where you have 75% popped kernels to 25% unpopped, which would be a 3-to-1 ratio, would correspond to 2 half-lives, which means I sealed that jar 14 minutes ago. And this is essentially exactly the same technique that people can use in real life, except we're not talking about self-popping popcorn. Instead, we're talking about the radioactive decay of isotopes. And just to give you a couple of examples, uranium-235 will decay into lead-207. That has a half-life of about 700 million years. And you also have uranium-238, and that will decay into lead-206, and that has a half-life of about 4.5 billion years. And there are a large number of such isotopes, but those are just a few examples. And instead of thinking about putting kernels in a jar and sealing them, you're thinking about the time since, say, the rock solidified, if you're looking at a rock. Because you're essentially, when it solidifies, you're sealing it off. There's not going to be any new material flowing in or of the existing material flowing out. You're just going to have all the atoms are locked into place there. And for organic systems, where you use carbon-14 dating, we're constantly taking in new carbon atoms all the time through food we eat and that kind of thing. So we're constantly restoring fresh new radioactive carbon in our body, which just occurs naturally in trace amounts. It's generated in the upper atmosphere, and then when the organic system dies, they're no longer taking in this fresh supply of radioactive carbon. So that's the same as sealing the jar. So essentially, by looking at the ratio of the radioactive isotope to its stable product, you can determine how many half-lives must have taken place, and therefore determine the age of that object. And that's the basic principle behind all of the sophisticated techniques that people use to do radioactive dating. It's just this simple process. It's as easy as popping popcorn.